Saxon's Calculus Lesson 8 is about Pythagorean identities and then trigonometric identities and cofunctions. So in Part A, Pythagorean identities, they remind you of three key formulas that I've referenced in other videos, which are sine squared plus cosine squared equals 1, tangent squared plus 1 is secant squared, and cotangent squared plus 1 is cosecant squared. Then in example 1, they say compute sine squared of 17 plus cosine squared of 17. Now at first glance, I feel like I need to graph the 17 degrees, but then I realize it's the same degree for both, and it's sine squared of a degree plus cosine squared of a degree. Oh, it just equals 1. 1 is the answer to example 1. Easy enough. Part B, trigonometric identities. Now at the bottom of page 55, they review three rules of how we should proceed with rearranging equations. So let's just review those. Step 1 is substitute any equivalent expression for all or any part of the original, the given one. So in other words, if it gave me secant squared and plugging in tangent squared plus 1 would make it helpful in solving, then do that. Everywhere I have a tangent, I'm going to write sine over cosine and so on. Number 2, multiply the numerator and denominator of any expression or the numerator and denominator of a part of any expression by the same non-zero quantity. In other words, if I multiply this side by something that equals a 1, I need to do the same to the other side of the equal sign to keep it in balance. And as long as it's not 0, which would change the value of the equation, and it's something that equals a 1, then that's good. And to equal 1, it's got to be the same thing, numerator and denominator. And finally, number 3, combine the terms that have equal denominators. In other words, obviously that's an algebra thing. You can't combine stuff unless it is common denominator. So now, example 2. Show that cosine squared plus 4 plus sine squared over 5 secant squared of negative x equals cosine squared. And all of those should have x's. I just didn't write them again. I was rushing. So I see that I have a cosine squared plus a sine squared. That's going to turn into 1. 1 plus 4 is going to make my numerator 5. Secant is the opposite of cosine. And when I have cosine with the negative, as we learned in the other lesson, we drop it. So this is basically secant squared, or 5 times the secant squared of the x, because the negative part doesn't matter. The 5's are the same top and bottom, so I basically am left with 1 over secant squared. And when you flip that over, or what is secant squared? The reverse of cosine. So we just said that 1 over secant squared is the cosine squared, so I just check mark in there. Yep, I accomplished what they wanted me to. Example 3. Secant to the 4th plus secant to the 4th times tangent squared over cosine to the 4th of a negative x equals secant to the 10th. Now this one I had to write the x with it even though I dropped it off the others because of the negative that's here. But in the very next step, as we just said, cosine doesn't keep the negative, so it's gone. So secant to the 4th can be factored out perhaps, and that would leave me 1, because I pulled everything from the first part, plus the tangent squared over, and then as we just said, this is cosine to the 4th, and it no longer needs the negative part. Now 1 plus tangent squared, 1 plus secant squared, so I can substitute this as a secant squared. Now when I multiply secant to the 4 times secant squared, multiply bases, add exponents. So that's going to give me secant to the 6th over top of cosine to the 4th. And what is that cosine the opposite of? Secant. Now, how did I know which way to go? I was looking at the answer of where they want secant in the final one. Otherwise, I might have converted secant to cosine. And so when I move this up, 1 over cosine is the opposite with secant. So that's actually putting another secant to the fourth up top. And again, when you multiply bases, add exponents, and that's what they wanted me to prove. Example 4, show that cosine squared secant squared minus cosine squared equals sine squared. All right, so again, I see I have a cosine in both. Let's factor it out. Cosine squared leaves secant squared minus 1. Now, secant squared minus 1, secant squared minus a 1 leaves me tangent squared. So I can substitute this as tangent squared. All right, cosine squared is kind of stuck as it is, but tangent squared can go to sine over cosine, and since those were both squared, that will remain squared for those. And then the cosine squareds cancel off. Ooh, yay. All I'm left with is sine squared, and I should put the thing back x, and that's what they wanted me to prove. All right, so now part C, cofunctions. Now this is where when we have a right triangle, and we talk about this angle being theta, then this one would be represented with 90 minus theta. And I can show that the sine of this one would be opposite over hypotenuse, so we'll call it O and H. And then this one, the O and H combination would be the adjacent over. So the sine of theta is the same as the cosine of 90 minus theta. And we don't think about them as naming them as cofunctions. We just kind of do them. But last year in Trig, you were provided with a list of things which said something like the sine of theta equals the cosine of 90 minus theta. And then they have it as equals the whatever the fraction is. I'm not going to do that because it's going to change per triangle. And then the same thing, cosine of theta would match with sine of 90 minus theta. And then your tangent of theta would be the same as cotangent of 90 minus theta. Now I could continue writing the other three, but I think you basically remember them. It is cotangent is the opposite of tangent 90 minus theta, secant is the opposite of cosecant 90 minus theta, and cosecant is the opposite of secant of 90 minus theta. Then they clarified this wording that basically means the sine or tangent or secant of the other angle. So if the original one is the theta, the other angle is what we're referring to here. All right, so then it reminds that there are 4 steps on the bottom of page 57 that you want to replace the functions that would have a negative theta in them, as we learned in the other lesson and we reviewed like here, with their positive version. Replace the 90 minus thetas, or in radians, that would be pi over 2 minus theta, with their cofunction. In other words, you don't want them with these, you want them with sine, cosine, or tangent, the basics. And look for forms of the Pythagorean identity, these, that can be replaced. And then replace tangent, cotangent, secant, and cosecant with their equivalent sine and cosine. So in general, you always want to get your equations down to the basic sine or cosine in order to simplify them. Now, example 5 says, show that cosine going with cosine of negative theta, and of course, because this one had the negative, it had the parenthesis, which is why they've changed it to the different multiply symbol, and then 1 plus tangent squared, and cosine pi over 2 minus theta equals sine of theta. All right, so we're going to try to follow the rules that they talked about. Can't do anything with this cosine, so I'm going to ignore it. This cosine is going to change to its positive form, which is just another cosine. 1 plus tangent squared, okay, if I have forgotten, 1 plus tangent squared is secant squared. So we're going to substitute that in, secant squared. And then this is the 90 minus theta, and it was for cosine. So if you need the reference, that means that cosine of 90 minus theta substitutes for sine of, and I used 90, although this was in radian, but we just took it down to is sine of. Now what happens when we multiply things here? Cosine squared, secant is the opposite of cosine, so 1 over cosine squared, and then we have the sine still there. Cosine squared and cosine squared are going to cancel off, and that just leaves me with the sine of theta, and that's what they wanted me to prove. Now, the final example 6. Show that sine squared of negative theta, and because of that, the multiply changed symbols. Cosecant squared minus 1 cotangent of pi over 2 minus theta, and that all should equal sine of theta cosine of theta. I don't know why I wrote them here when I didn't write them in the other places where they weren't necessary, but that doesn't matter. Okay, so the sign with the negative means I put it out front, so it's negative sine squared. Cosecant squared minus 1, cosecant squared minus 1 is cotangent squared. I'll put that in parentheses. And then our cotangent of 90 minus theta, and that's one I didn't write down, but if I, well, it's cotangent, no, tangent, tangent, and it wasn't squared, so it's just tangent. And now, let's see what we can do here. Cotangent and tangent should be written in their sine over cosine forms. So negative sine squared, and that's the opposite of tangent, so it's cosine over sine, and both are being squared. And then tangent is sine over cosine. Now, sine squared and sine squared are going to cross off. That's leaving me negative cosine squared. Oh, wait, I see it. There's a cosine, and a cosine squared can drop down to only 1, so it's no longer squared. So I have negative and cosine and sine, and we've gotten rid of all of the denominators. And that's what I want, except for this change in sign. Did I miss one somewhere? Oh, yes. I did what they said don't do. I questioned it as I wrote it, and then I thought, oh, I'll fix it in a second. Because this was a negative with this squared, if I pull this to the front as I should with the sign, I'm ignoring the fact that the squared actually overrides positive and negatives, so it took the priority. This never existed here or here because the squared removed the negative. Now it is just cosine of theta and sine of theta, and the order doesn't matter, so yes, we're good to go. And if I had looked over here in their example, I would have seen there, yes, no, do not pull the negative out. So if you were following in the book, you would have caught that before I did.